Next, sulfur and its compounds. Sulfur was discovered by the ancient Chinese in the prehistoric period, but was recognized as an element in the second half of the 18th century. It was used as a fumigant in ancient Greece, and it's what is referred to in the Bible as brimstone. It is a yellow non-metallic solid occurring freely in the United States, Italy, and Japan. Sulfur compounds also occur naturally in petroleum, coal, and natural gas. Sulfur also occurs as hydrogen sulfide and sulfur dioxide in hot springs and in volcanic gases. In living things, sulfur occurs as a compound of some proteins. With atomic number 16 in group 6 and period 3 of the periodic table, sulfur has an electron configuration of 286 and a mass number of 32. Most common valency is 2, but rarely a 6 when it combines with more electronegative elements, for example oxygen and fluorine. Extraction of sulfur. The fresh process. The sulfur beds lie beneath layers of clay, sand, and limestone, which makes open mining impossible due to the risk of collapse. The fresh process is based on the fact that sulfur has a comparatively low melting point. The fresh pump, consisting of 3 concentric pipes, is sunk deep into the sulfur bed. Superheated water at about 170 degrees Celsius under pressure is pumped into the outermost pipe. The water enters the sulfur bed and melts the sulfur present. Compressed air under a pressure of 20 to 25 atmospheres is pumped through the innermost pipe. This forces the mixture of the water and molten sulfur to gush out through the middle pipe. This mixture of water and molten sulfur is collected, and on cooling, about 99% pure sulfur gets separated. Allotropes of sulfur. Solid sulfur exists in 2 different crystalline forms. These are called rhombic sulfur and monoclinic sulfur. Both forms are made up of pure sulfur. They differ in the shape and heat stability of their crystals. Rhombic sulfur, also called alpha sulfur, consists of octahedral shaped crystals. It is only stable at temperatures below 96 degrees Celsius. Monoclinic sulfur, also called beta sulfur, consists of needle-shaped crystals. It is only stable at temperatures above 96 degrees Celsius. Thus, below 96 degrees Celsius, crystalline sulfur exists in the rhombic form, and above 96 degrees Celsius, it exists in the monoclinic form. The temperature 96 is in this case called the transition temperature. When a substance exists in several different forms in the same state, it is said to show allotropy. The different forms are called allotropes. The allotropes have the same chemical properties but different physical properties. Physical properties of sulfur. Sulfur is a yellow odorless solid which is insoluble in water but soluble in organic solvents like carbon disulfide and methylbenzene. At ordinary temperature, sulfur exists as a solid covalent substance. Each sulfur molecule comprises of a crown-shaped ring consisting of 8 sulfur atoms. The atoms are linked by strong covalent bonds forming an S8 molecule. Individual molecules are linked to one another by weak intermolecular forces such as van der Waals forces. The molecules are packed regularly, forming crystals, and are present in both rhombic and monoclinic crystals. When sulfur is heated, it melts at 113 degrees Celsius into a clear pale yellow liquid that flows easily. At this point, the intermolecular forces are broken, separating the individual molecules, resulting in liquid sulfur. On further heating, the liquid darkens, becoming reddish-brown, very viscous and hardly flows. This is because as heating continues, some of the covalent bonds break, leading to the formation of long chains of atoms. The chains get entangled, causing the liquid to become viscous and dark. In fact, at some point the test tube can be inverted without the sulfur pouring out. As heating continues, the liquid becomes black and flows easily once again. This is because more covalent bonds break, resulting into smaller molecules which are less entangled. This makes the liquid less viscous. At a temperature of 444 degrees Celsius, the liquid will boil, forming a brown vapor because the molecules become smaller and smaller. In fact, at 1000 degrees Celsius, sulfur molecules will exist as S2 molecules, and if the temperature is increased further, single atoms of sulfur will form. But anyway, when boiling sulfur is suddenly cooled by pouring it into cold water, see what happens. The product is elastic and is called plastic sulfur. If this plastic sulfur was left for several days at room temperature, it will harden into rhombic sulfur. Good. Now we look at the chemical properties of sulfur. Reaction with air. Sulfur melts and catches fire, burning with a blue flame. It burns in pure oxygen with a brilliant blue flame. In either case, sulfur combines with oxygen to form sulfur dioxide, which has a choking smell. Traces of sulfur 6 oxide are also formed. The sulfur dioxide dissolves in water to form sulfurous acid. Reaction with iron. When a mixture of iron and sulfur is heated, it starts to glow. The glow continues and increases in intensity even after the heating is stopped. This shows that the reaction is exothermic. A black solid of iron 2 sulfide is formed. Other metals like zinc and copper also react with sulfur when heated, forming metal sulfides. Sulfur does not react with dilute acids. However, concentrated sulfuric acid oxidizes sulfur to sulfur 4 oxide. Again, concentrated nitric acid oxidizes sulfur to sulfuric acid and is itself reduced to nitrogen 4 oxide. Sulfur is used in the manufacture of sulfuric acid, which has a large variety of industrial uses. Vulcanization of rubber, that is hardening of rubber to tough substance that can be used to make tires. Manufacture of gunpowder, explosive, matches and fireworks. Manufacture of sulfur drugs, insecticides and fungicides. Manufacture of calcium hydrogen sulfide for bleaching wood pulp. Manufacture of carbon disulfide. Manufacture of sodium thiosulfate, which is used in photography, and manufacture of artificial hair dyes. Sulfur 4 oxide. Sulfur 4 oxide is commonly called sulfur dioxide and is a gas at room temperature. It is formed when sulfur burns in air. The gas is released in the atmosphere when sulfur-containing substances such as coal and oil are burned. For this reason, the air of industrial cities contains trace amounts of the gas. In the laboratory, sulfur 4 oxide is prepared by reacting copper tannings with sulfuric acid. The apparatus required and their arrangement is shown here. Copper tannings are taken into a round-bottomed flask. Concentrated sulfuric acid is poured into the thistle funnel until it covers the copper tannings. The flask is gently heated. Reaction takes place and sulfur dioxide is evolved in a continuous stream. Sulfur 4 oxide, being heavier than air, is collected in a gas jar by upward displacement of air. The gas can be passed through concentrated sulfuric acid to remove any moisture if required dry. Sulfur 4 oxide can also be prepared using sodium sulfide and hydrochloric acid. The apparatus setup is similar. Sulfur 4 oxide is a poisonous and colorless gas with a pungent choking smell. It is 1.5 times denser than air. It is very soluble in water. In fact, 1 volume of water dissolves 700 volumes of sulfur 4 oxide. It condenses into a colorless liquid at -10 degrees Celsius. Chemical properties of sulfur 4 oxide. pH. When a wet blue litmus paper is inserted in a gas jar of sulfur dioxide, it turns red, indicating the gas is acidic. And this happens because sulfur dioxide combines with water to form sulfurous acid. Bleaching action of sulfur 4 oxide. Sulfur 4 oxide acts as a bleaching agent and bleaches flower coloring matter in the presence of moisture. You can observe here how a moist flower loses the color. The bleaching property of sulfur dioxide is due to its reducing action. The coloring pigment on exposure to sulfur dioxide gets reduced to a colorless compound. On standing in air, the colorless reduced product is reoxidized and regains the original color. Bleaching of sulfur dioxide is therefore of a temporary nature. The material to be bleached must be wet. This is because water is required to form the sulfite ions, which are responsible for the bleaching action. Reducing action of sulfur 4 oxide. Sulfur 4 oxide only displays reducing properties when it is dissolved in water. Under these conditions, it exists as sulfurous acid, which dissociates into sulfite and hydrogen ions. The sulfite ion can be oxidized to sulfate ion by obtaining an oxygen atom from another compound, like water. During this reaction, 2 electrons are released. The electrons can be accepted by an oxidizing agent, for example potassium dichromate 6 or potassium manganate 7, which becomes reduced in the process. When sulfur 4 oxide gas is bubbled into a solution of acidified potassium dichromate 6, the color of the solution changes from orange to green. This is because the orange dichromate 6 ions are reduced to the green chromate ions. The electrons necessary for the reduction of dichromate 6 ions are supplied by the sulfite ions, which are in turn oxidized to sulfate ions. When sulfur 4 oxide gas is bubbled into a solution of acidified potassium manganate 7, the solution changes from purple to colorless. This is because the purple manganate 6 ions are reduced to manganese ions by the sulfite ions. Although manganese ions are pale pink in color, their concentration is very low for the color to be observed. The sulfite ions are in turn oxidized to sulfate ions. When sulfur 4 oxide gas is bubbled into a solution of iron 3 sulfate, the color of the solution changes from brown to pale green, and this is because the brown iron 3 sulfate is reduced to light green iron 2 sulfate. Sulfur 4 oxide is itself oxidized to sulfuric acid. Action of sulfur 4 oxide. When a burning magnesium ribbon is placed in a gas jar of sulfur 4 oxide, it continues to burn. A mixture of white magnesium oxide and yellow sulfur is deposited in the jar. Oxide gas does not burn nor support combustion. However, the heat produced by a burning magnesium ribbon decomposes it into sulfur and oxygen. Magnesium continues to burn in the oxygen, forming magnesium oxide. If a mixture of carbon and sulfur 4 oxide gas is heated to a temperature about 1000 degrees Celsius, carbon 4 oxide and free sulfur are formed. This reaction is used to obtain sulfur from industrial fuel waste. When a jar of hydrogen sulfide gas is inverted over a jar of sulfur 4 oxide gas containing a little water, a yellow deposit of sulfur is formed on the sides of the gas jars. In this reaction, sulfur 4 oxide is reduced to sulfur, while hydrogen sulfide is oxidized to sulfur as well. Both sulfur 4 oxide and hydrogen sulfide are reducing agents. However, hydrogen sulfide is a stronger reducing agent. There would be no reaction that will take place when the jar containing sulfur 4 oxide is completely dry. Sulfur 4 oxide is used as an intermediate in the manufacture of sulfuric acid by the contact process. It is used for bleaching wool, straw, milk, and this cannot be bleached using chlorine as they react with it. It is used for the manufacture of calcium hydrogen sulfide, which is used for bleaching wood pulp in the manufacture of paper. It is used in small concentrations as a preservative for fruit juices. Here, it acts by reacting with any oxygen present and thus preventing the growth of bacteria and fungi that may promote fermentation of the juices. Dry sulfur 4 oxide is used as an insecticide for mosquitoes, flies and fleas, and as an anti-vermin for rats. liquid sulfur 4 oxide is used in refrigerators. Sulphur 6 oxide. Sulphur 6 oxide is commonly called sulfur trioxide and is formed when a mixture of dry sulfur 4 oxide and dry oxygen are passed over heated catalyst. Sulfur 6 oxide and oxygen are dried by passing through concentrated sulfuric acid. The dry gases are then passed over heated vanadium pentoxide or vanadium 5 oxide or platinized asbestos and react to form sulfur 6 oxide. The latter is passed into a wash bottle placed in an ice bath. Here it is deposited as sulfur 6 oxide crystals. Anhydrous calcium chloride protects sulfur trioxide from attack by atmospheric moisture. Sulfur 6 oxide freezes at 17 degrees Celsius and boils at 44 degrees Celsius. It is therefore a liquid at room temperature. It combines vigorously with water forming sulfuric acid. Industrial manufacture of sulfuric acid. The contact process. Sulfuric acid is used in a wide range of processes. It is used in metal reactions, drugs manufacture, paints, and making of explosives. Now here is a schematic animation of the major parts of the contact process. At first, sulfur 4 oxide is produced either by burning sulfur or burning any sulfur-containing ores such as iron pyrite or zinc blende. The sulfur 4 oxide and excess air are then passed through a purification chamber where dust and other impurities, especially arsenic compounds, are removed. This is achieved mainly through electrostatic precipitation. Purification is important because the catalyst used at a later stage is highly susceptible to poisoning. The mixture of sulfur 4 oxide and air is then passed into a catalytic converter. This contains vanadium 5 oxide catalyst distributed over layers of silica gel, which acts as the carrier. Originally, platinized asbestos was used as the catalyst. Although it is more efficient than vanadium 5 oxide, it is more expensive and highly susceptible to poisoning. In the catalytic chamber, sulfur 4 oxide reacts with oxygen, forming sulfur 6 oxide. At a temperature of between 400 and 500 degrees Celsius and a pressure of 1 to 2 atmospheres, a 98% yield of sulfur 6 oxide is achieved. From here, the gases are then passed into an absorption tower. This is packed with ceramic rings through which concentrated sulfuric acid flows. Here, sulfur 6 oxide is absorbed in the concentrated sulfuric acid. The result is a highly viscous oily liquid called oleum or disulfuric acid. Sulfur 6 oxide is not absorbed directly into water because the reaction is highly exothermic. This causes the solution to boil, forming a mist of tiny droplets which are dangerous and condense slowly. Oleum formed in the previous stage is mixed with a carefully calculated quantity of water to give concentrated sulfuric acid. This contains 98% sulfuric acid and 2% water. Pure sulfuric acid is a colorless and odorless oily liquid. This explains why it is commonly called oil of vitriol. It has a density of 1.84 grams per cubic centimeters, freezes at 10 degrees Celsius and boils at 338 degrees Celsius. It dissolves in water with evolution of a large amount of heat and has no effect on litmus paper. Note that concentrated sulfuric acid is highly corrosive and should be handled with care. It will cause serious burns if it gets into contact with the skin. When diluting sulfuric acid and any other acid, always pour the acid into the water and never water into the acid and stir continuously. If water is poured into the acid, the heat evolved causes water to boil, splashing the acid. The chemical properties of concentrated sulfuric acid are different from those of dilute acid. Chemical properties of concentrated sulfuric acid. Dehydration properties. Concentrated acid has a very high affinity for water. When added to a crystal of blue hydrated copper 2 sulfate, it draws the water of crystallization from the salt, leaving the white anhydrous copper 2 sulfate. When concentrated sulfuric acid is added to sugar, a frothy and black mass of a substance is formed. The black substance is carbon. It appears frothy because of trapped steam. Oxidizing properties. Hot concentrated sulfuric acid is a strong oxidizing agent. It oxidizes both metals and nonmetals. Metals are converted into their sulfate salts. Nonmetals are converted into their oxides. Sulfuric acid is itself reduced to sulfur 4 oxide and water. For example, copper tannings react with the acid, forming a blue solution of copper 2 sulfate. In this reaction, metallic copper is oxidized to copper 2 ions. The 2 electrons are taken up by sulfuric acid, which gets reduced to sulfur 4 oxide and water. Copper is the reducing agent in this reaction, and concentrated sulfuric acid is the oxidizing agent. Zinc reacts in a similar way to copper. In this case, however, zinc sulfate and sulfur 4 oxide are formed. Hot concentrated sulfuric acid oxidizes almost all metals with the exception of those that are very low in the reactivity series, such as gold and platinum. Displacement reactions. Hot concentrated sulfuric acid will displace hydrochloric acid and nitric acid from their salts. Both these acids are more volatile than sulfuric acid. When a mixture of a chloride salt is heated with sulfuric acid, hydrochloric acid vapor distills out. With nitrates, nitric acid vapor distills out. Physical properties of dilute sulfuric acid. Dilute sulfuric acid is a colorless and odorless liquid and turns a blue litmus paper red. Dilute sulfuric acid is a diabasic acid which dissociates into two stages upon addition of water. It first dissociates into a hydrogen ion and a hydrogen sulfate ion. The hydrogen sulfate ion may dissociate further into hydrogen ion and sulfate ion. In very dilute solution, the acid is completely dissociated. As such, it has a high concentration of hydrogen ions and is therefore a strong acid. It is the hydrogen ions that give an acid its acidic properties. Note that pure sulfuric acid is a covalent compound and is therefore not dissociated into ions. For this reason, it doesn't show the properties of a strong acid. For example, it does not turn a blue litmus paper red, it does not produce hydrogen when it reacts with metals, and it does not conduct electricity. Reaction with metals. Effervescence is observed when magnesium is added to dilute sulfuric acid, indicating a reaction that liberates a gas. The observation shows that dilute sulfuric acid reacts with metals higher in the reactivity series, forming hydrogen gas. With copper turnings, no reaction will take place, and this is because copper is lower than hydrogen in the reactivity series. Silver, mercury and gold would behave in a similar manner. With calcium granules, a reaction starts but soon stops. This is due to the formation of insoluble calcium sulfate, which coats the metal, preventing further reaction. Lead and barium behave like calcium because their sulfates are also insoluble. Metals that are very high in the reactivity series, for example potassium and sodium, react violently with dilute sulfuric acid. The experiment should never be conducted in the school laboratory. Reaction with soluble bases or alkalis. When sodium hydroxide is added to dilute sulfuric acid in the presence of phenolphthalein indicator, the mixture changes from colorless to red. This shows that the acid has been neutralized by the alkali. A salt and water are formed. A similar observation is made with potassium hydroxide. Reaction with insoluble bases. When copper 2 oxide, which is black in color, is mixed with dilute sulfuric acid, it dissolves, forming a blue solution of copper 2 sulfate. This is also a neutralization reaction in which a salt and water are formed. Reaction with carbonates and hydrogen carbonates. Effervescence occurs when dilute sulfuric acid is mixed with sodium carbonate or sodium hydrogen carbonate. Carbon dioxide is liberated, and this can be tested by bubbling it through lime water, and a white precipitate will be formed. Last compound, hydrogen sulfide. Hydrogen sulfide forms when two hydrogen atoms combine with one sulfur atom. It is produced as an unwanted product during industrial operations. Hydrogen sulfide is also created biologically over time by decaying organic materials often deep underground. It is soluble in water, oil, and gas. Hydrogen sulfide, also called sour gas, sulfurated hydrogen or sewer gas, can be found in concentrations ranging from trace amounts presenting no hazard to very large amounts which are immediately dangerous. Human senses are not entirely reliable for detection. First, hydrogen sulfide is colorless, so you can't see it. In low concentrations, you might smell or even taste the gas. Hydrogen sulfide is sweetish on the tongue, but to the nose it's pretty foul with odor like rotten eggs. But at high concentration of the gas, the sense of smell is quickly deadened. Hydrogen sulfide is denser than air, so it collects in low places. In addition, hydrogen sulfide is highly flammable. In the laboratory, hydrogen sulfide is produced by the action of dilute hydrochloric acid on iron 2 sulfide. A KCSE apparatus is used for continuous and regular supply of hydrogen sulfide gas. It consists of 3 globes. 2 lower globes are fused together and an upper one containing a long neck fixed into it. Iron 2 sulfide is placed in the middle globe and is connected with a stopcock for the passage of the gas. Acid is poured from the top. When the stopcock is open, the acid comes in contact with the iron 2 sulfide. A reaction takes place and hydrogen sulfide is generated. When the stopcock is closed, hydrogen sulfide exerts pressure on the acid, which rises high in the upper globe, and further reaction is prevented. Reaction can again start when the cork is again opened. Physical properties of hydrogen sulfide. Hydrogen sulfide is a colorless gas. At low concentration, hydrogen sulfide has a very offensive odor similar to the smell of rotten eggs. At high concentration, the odor cannot be detected because hydrogen sulfide kills the sense of smell. Pure hydrogen sulfide is about 20% heavier than air. It has 3 times the flammability of natural gas, and this means that a fire or an explosion can occur in the presence of even a very small amount of hydrogen sulfide. When ignited, hydrogen sulfide produces yet another toxic gas, sulfur 4 oxide, which is hazardous when inhaled. Hydrogen sulfide is soluble in water and organic solvents, but as the temperature increases, it becomes less soluble and hydrogen sulfide gas breaks out of solution. Hydrogen sulfide is highly corrosive to metals, so pipe valves and other equipment should be designed for hydrogen sulfide and properly maintained. Iron 2 sulfide may be deposited inside the pipes or vessels where hydrogen sulfide is present. Chemical properties. Combustion. Hydrogen sulfide burns in excess air with a blue flame, forming sulfur 4 oxide. In a limited supply of air, free sulfur is deposited. Reducing properties of hydrogen sulfide. Hydrogen sulfide is a strong reducing agent. During the reduction process, it is oxidized by loss of hydrogen to free sulfur. When dissolved in water, hydrogen sulfide ionizes in two stages as shown by these equations. The two electrons can be accepted by an oxidizing agent which becomes reduced. Free sulfur is deposited as a yellow substance. When hydrogen sulfide is bubbled through acidified potassium manganate 7 or potassium dichromate 6 solutions, they are reduced by the gas. With potassium permanganate, the solution changes from purple to colorless. And with potassium dichromate, the solution changes from orange to green. When hydrogen sulfide gas is bubbled into a solution of iron 2 chloride, the color of the solution changes from yellow to pale green, and this is because the yellow iron 3 chloride is reduced to light green iron 2 chloride. Hydrogen sulfide is itself oxidized to hydrogen chloride and frees sulfur. Hydrogen peroxide is also reduced to water. Sulfuric acid is reduced to sulfur. For this reason, concentrated sulfuric acid cannot be used to dry the gas. Dilute nitric acid is reduced to nitrogen 4 oxide gas. Bromine water, which is orange in color, is reduced to a hydrogen bromide solution, which is colorless.
Choose a path, choose a direction, choose your day, choose your hours, choose to network, choose a strategy, choose to create, choose your media, choose to care, choose to inspire, choose to listen, choose to learn, choose to train, choose to compete. Newcastle College, why choose anywhere else?